So I don't need to.
I'll give a little introduction here once he starts recording.
I don't need to unmute myself, right?
No, you should be able to hear through the mic. Okay, so good morning, everyone. Welcome to our next installation of our IQS seminar series. I'm happy to introduce Bibek Bhandari. Bibek comes to us originally from Nepal. He did his PhD at the Scuola Normale Superiore in Pisa, Italy, and he's been working with us, my group, for the past 2 years now, doing a lot of work on quantum thermodynamics and now getting into quantum computing. So quite versatile and talented postdoc. So Bibek, the floor is yours.
Thank you. So this is a presentation is like, I would say, based on a work which is like half done. So I would have some results, but I would also have some questions in the middle, which might not be answered. So just be prepared to not get answers to all the questions that I would present. So I'm still working on this thing. So this is the work we have been doing since last year on quantum feedback thermal machines and what is the role of measurement and feedback in quantum thermal machines. That's the basic idea about it. And so going on to literature, we have some work done on this thing with Khan and Srinath. So it's recently accepted in PRA, and it's like thermodynamics of quantum measurement and the demon zero of time. So this work is basically we finished this work, but we are also pursuing a different work where we are studying quantum feedback thermal machines in particular. And this is in collaboration with Paolo, and this is under preparation. So mostly like half of the talk would be on the first part of the paper, and the rest would be the next part. And in the next part, there will be some answers and some questions without answers. So we're just looking for some directions that we can pursue. And so just like I usually begin with this slide when we say quantum thermal machines, what do you mean by quantum thermal machines? What is heat transport? What is energy transport? So usually this kind of device is what we have is a nanoscale system S, which can be also a quantum system S. And this quantum system S is attached to two different leads here, left and right. And if I heat one of the leads, let's say the left lead, and cool one of the leads, let's say the right lead, then there is a temperature gradient from left to right, and heat flows from hot to the cool lead, right? So we have one direct motivation to obtain energy or heat transport in these kind of devices. Other possible way would be to put a potential gradient and also study particle transport, energy transport in a similar manner. So this has been quite explored in recent decades with the advent of nanoscale systems, like with the advent of controlling heat and particle transport experimentally in lab for nanoscale systems. But what we are interested is, we are also interested in measurement. So what we are seeing is that we have a system, a two-level system, which is attached to a lead. Let's say I say L, which is a reservoir. It has a fixed temperature T, and it's macroscopic in dimension, whereas the two-level system is a nanoscale system. We just worry about the first two levels, it's a qubit. And what we are doing is that we are continuously measuring the qubit. At the same time, we are attaching it to the path L. So the Hamiltonian for the qubit will be given by epsilon 0, 1, 1. So when it's in the excited state, the energy is epsilon 0. When it is in the ground state, I say the energy is 0 as a reference. And the measurement observable, or the operator I'm measuring of the qubit, is X operator, which has like sigma X form here. And with some Maxwell equation calculation, I can immediately obtain the heat current flowing out of path L, which includes the contribution both due to measurement probe as well as the lead L. And we can see that in this kind of situation, the heat current is always negative, meaning there is no way one can cool the path L if you are continuously monitoring as well as continuously attaching the path to the system. So the general idea about how can we cool this kind of system if you can't cool without anything else would be to include something more, right? So what we are trying to do is that, let's say, if we have some feedback, or if we can attach and detach the system, so those kind of stuff, and we try to see if we can achieve.
So maybe point out here, Bibek, so the only role of the measurement in this equation is just in this gamma m term.
Yes.
That's right. And so,
Yes. So we are just looking at the average dynamics produced by the measurement.
so if the rate went to 0, you wouldn't have any heat flow, but
No.
But now you basically just have heat flowing from the measurement device into the left lead.
Yes. The heat is just because you can't have a heat flow just because of one source, right, or one sink. You'll be violating the second law of thermodynamics. So the measurement probe somehow it gives you a separate environment in a sense. So what we can say that measurement inevitably leads to dissipation in this kind of system or heating, and feedback should be applied to obtain cooling. So that's the motivation behind why we are talking about feedback. So on the first part, I'm going to talk about the recent paper that we had with Khan and Sridhar. And in this paper, what we studied was it's a quantum feedback in single qubit system. So what we have is on the right-hand side, we have a qubit, which is represented as a block sphere here. And this qubit is attached to an environment R. And at the same time, there is a daemon in the which is quite evident, I guess, who is monitoring the measurement record, and he does his tricks based on the measurement record so that we can obtain cooling. I will go through the details, but here I've outlined the steps. I will go through each step in the next slide. So step one would be to thermalize the qubit. Then we will do a measurement. When we thermalize the qubit, it just has the G component, and we do an X measurement so that we get rotated in the X direction. You can see from the yellow arrow in the block sphere. Now what you do is that you apply feedback and bring it back to the G axis, and the remainder of the energy is extracted. But let's go in detail on this thing. So what is the thermalization step? So what we have is that we have the qubit, and there is no measurement for now. We have the qubit, and we just have the reservoir. We put the qubit in contact with the reservoir. And so if we have the Hamiltonian at 0, and then the density matrix with Hamiltonian at 0, which is diagonal, would be immediately given by rho ITH, where G is the partition function, which just sums over all the possible energies. It just normalizes the density matrix. And based on that, we can have the initial energy of the qubit. If we have the density matrix, if we have the Hamiltonian, we know the trace of the Hamiltonian with rho will give you the energy E0, and G0 is just a function of the Bose distribution. So we have the energy of the qubit. So the main thing is that in the beginning, when we thermalize the qubit, we know what is the energy of the qubit. That's the main message here. Next, measurement. So what we want to do is that we want to perform a measurement which has like a sigma x component and an identity component. The sigma x component rotates the qubit along the sigma x direction, but we have this term kappa, which is dependent on gamma and delta t, and gamma gives the measurement strength and delta t is the measurement time. So what we are trying to do is we're trying to do a weak measurement here. We don't want to do a projective measurement, but a generalized measurement, which in certain limit goes to a strong case. When kappa goes to 0 or 1, we get a strong measurement. When kappa goes to half, then you can see that M would be just an identity, and you don't get any information out of it at all. So depending on the values of kappa, one can go from very weak measurement to projective measurements. And the state of the qubit after measurement would be given by the simple formula, which takes into account the forward measurement probability, in the sense that we are going forward in the measurement direction. I will tell you why I'm writing this as forward measurement probability, because we can also have backward measurement probability, in the sense that if we try to reverse the information obtained during measurement, or if we try to reverse the measurement by doing a time reversal measurement, then we see that M plus would become M minus in the time reversal domain, and we get this PB plus minus based on the forward measurement. So PB is just a backward measurement if you obtain a forward measurement. What is the probability of obtaining a particular backward measurement if you do one forward measurement? And we define the arrow of time Q as a logarithm of forward as well as backward measurement. We call it error of time because it determines whether we are going forward or backward in the measurement direction. And interestingly, in this scenario, this error of time, it doesn't depend on anything except kappa, which gives you the measurement strength. And on the top part, I am calculating the energy of the qubit after measurement because I know the density matrix after measurement, right, by using the cross operators. So I can calculate the energy of the qubit after measurement. I obtain the result presented here. And it looks that the energy of the qubit after measurement depends only on the initial energy of the qubit and the error of time. It doesn't. So it's like the error of time gives you the irreversibility in the measurement process, and somehow it enters in the energy of the qubit as well as other thermodynamic parameters that we will see later. So now, after we have done this measurement, so in the figure, to be more clear, we can see it from figure below there. In the step A, what we have is that we have a thermalization. So the arrow is pointing in the negative z-axis. We have the qubit in the thermal state. Now what we do, the daemon does a measurement. What is the x component of this qubit, right? And it tries to see what happens when it does this x measurement. The qubit rotates along the Bloch's pair. You have an x component along with z component. Now, what is the final Bloch length when you do this measurement? It's given by gf, which is just the normal of x and z. And what the daemon does is just it rotates the Bloch vector back to the z-axis. But now you can see that the red arrows, they have different dimensions, they have different scales, so that you can have some energy that you can extract from this system. In summary, what you will have is that you will have smaller energy of the qubit compared to the previous energy. So the difference of energy is negative. And then when you put the reservoir back, you get the energy back to the reservoir. So reservoir is being put in that sense. So extract some work from the qubit by this process. So you see here, epsilon A minus, so the difference in energy should be positive in the sense that epsilon A minus epsilon C should be positive, and it's given by that term there. And that is the amount of work that extract from the qubit, from this kind of feedback-based device. And this depends, so in a way, one sees that depends only on the error of time parameter q heavily, and also on the initial state of the qubit. So that's what motivated us to write this paper, because we saw that every thermodynamic parameter, as well as the energy of the qubit after measurement as well as feedback, that they depend only on initial values as well as error of time, nothing else. So that's why the title of the paper that is thermodynamics of quantum measurement and how it depends on daemon's error of time. Now so the entropy production now, what is the entropy production of all this process during this process, or the entropy production due to measurement would be given again in terms of the error of time parameter q, and as well as the final Bloch length zf, which depends on q again, and the entropy cost of information. So during this process, when daemon acquires information, he has to erase the information back, right? So which cost him kV log to amount of information. So there is a cost to acquire information in thermodynamics. You can't acquire information for free, and this cost is given by kV log 2. Now, if you take into account all these parameters, then you can calculate the coefficient of performance of the refrigerator or your device that's being cooled. And this is given in terms of the heat extracted, which is on the numerator. It is the amount of heat extracted from the reservoir, and it is the difference of final energy minus the initial energy of the qubit. That's the amount of heat you extract from the qubit, divided by the cost of performing the measurement and the feedback. So what is the total power input, work input to obtain that refrigeration? And it is given in terms of the energy of the qubit after measurement, like the energy to provide measurement, to do the measurement, as well as the energy cost of information. So here we plot the coefficient of performance as a function of measurement strength. And you see for kappa equals to 0.5 when there is no information obtained from the qubit, or there is like the weakest measurement or no measurement at all, then you don't have any, the coefficient of performance goes to 0. So it's not a refrigerator because You're not acquiring any information. You are not doing anything with the qubit. So you're not getting any work extraction. But as you move farther from like 0.5, you go closer and closer to strong measurement or projective measurement, right? Then you get more and more work extraction or like more information from the qubit, more extraction. But the most interesting thing is that the best cooling is not obtained at projective limit. So the best cooling is obtained somewhere in the middle between projective and the weak. So so that it shows the maximum for some value of kappa, which is kind of interesting. And we also plot the entropy production as a function of the error of time. And you can see that when Q goes to zero, zero means that it's perfectly time reversal. There is no irreversibility, and you don't have any entropy production, right? You just have the entropy production due to acquiring information. Other than that, delta Sm goes to zero. But as you move along the Q axis, you acquire more and more information, or you become more and more irreversible, then you have higher entropy production due to measurement. So that was the case with discrete measurement. We also performed like the continuous measurement case with where we choose this continuous operator for forward and backward measurement. And in this case, delta t is the time allocated for one measurement. If you have very small time delta t, you are doing a weak measurement. When delta t goes to zero, no measurement. And if you have very large delta t, then you're doing a very strong measurement because you're providing enough time for the experimentalist to get the right information out of the system. And tau is the characteristic measurement time, and R is the measurement record obtained. But in this case, we're just doing numerical simulations using random samplings of Gaussians centered around the eigenvalues plus minus 1. So these are the main results of our paper. So we could, in the continuous measurement case, we could calculate analytically the work distribution as well as distribution of heat in these kind of devices. So we have some analytical results which gives you how the work and the heat will be distributed when you do this random sampling within the spectra. And you see that in the right plot, the red dashed line are theoretical plots, and the boxes are just the numerical simulations. And you see that the extracted plot, the theoretical plot matches exactly with the histogram for the numerical simulation. So it's, the analytic results are in perfect match with numerical results. The same is the case for the distribution of the measurement energy. So yeah, so this was the first part where I showed you the results from our recent paper where we studied feedback and measurement and both continuous and discrete measurement and how you can obtain cooling in single qubit. And now we are motivated to go to 2 qubit limit and to see what happens in the 2 qubit limit, right? So yeah, just a caution, this is like still work in progress, so I would not have the results. I will just show you like where I am on this thing. So what I'm trying to do is that I'm trying to see what happens like still one bath and 2 qubits, and then we measure both of the qubits. And the measurement can be performed on each of the qubits separately. So we have like 4 different cross operators instead of 2 here. One simple scenario that we can consider is a GZ coupling between the 2 qubits, where like still we have the diagonal elements, we don't have any off-diagonal elements, so everything calculation follows very simple manner. We have the initial density matrix and initial energy of the qubit, similarly as in the case of single qubit case. And we can have like 2 simultaneous measurements, one after the other in this case, because we have 2 qubits. And we just follow the same language as we followed in the previous one, except we have simultaneous measurements now. We perform measurement in the second qubit, and we perform measurement on the first qubit after that, and try to see what happens to the state of the qubit. And yeah, so what happens to the state of the qubit? What is the error of time? I have a question there because I don't know what is the error of time in this case. And we also try to see what is the energy of the qubit of the measurement. And the basic idea is if you do X measurement in both qubits, they get rotated along the X direction. Now what you do is that you do the rotation of both qubits. but there's a thing. There's a coupling between the two qubits that will interfere, right? So the cooling factor would be, I don't know, it can be greater than the sum of the two qubits or like lower than the sum of two qubits. So that's what we are interested in. So that's what I'm mentioning here. So both qubits will acquire an X component. And what we will do is that we will rotate the qubits in the Z direction, and we have the final states. And after that, we'll extract energy from the two qubits. The next thing that we could do in this case would be just to see sigma x coupling between the two qubits, but then it would be a difficult problem in the sense that you have off-diagonal terms. You either work in the local regime or in the global regime, in the sense that you have to do perturbation, right? Respect to whether the coupling between the two qubits is large or the coupling between the qubit and the bath is large. So here I'm trying to prefer the global regime where I have a strong coupling and try to see what happens in this weak measurement regime, how these things depend, and how the cooling performance depend as a function of measurement strength. So, but this thing is still in progress, so I don't have much results. Now, this is part 3, where I have a couple qubits, but I also have like 2 environments now. And these environments can be detached, so they are always coupled to the qubit. So now I don't have the liberty of throwing away the environment. I just couple the environment with the qubits. And I have some results in this part though. So in this case, what we can use is that we can use the cross operator treatment is equivalent with this treatment, so it's not something very new. And what we can do now is that we can just write the dynamics of the density matrix in terms of Lindbladian operators. So the first term there, alpha, sum over alpha equals to LR, gives you the contribution due to the baths, left and right. And the second term there gives you the contribution due to measurement, which is LM. And so I have given the form of LM rho, and but I don't think they are very important. They're just remember that L alpha would mean the contribution due to bath, and LM would be contribution due to measurement. And but the point was that that thing was for efficient measurement. Suppose that our measurement is not efficient, and we have to include the inefficiency of the experimentalist in detecting the photons or like those kind of scenarios. Then if you include that inefficiency, the master equation or the equation of motion would look like this. And the measurement record that you obtain would be given as a function of the average of the measurement operator that you are measuring. Here it is x plus a stochastic term, which gives you the noise background. So what we are doing is that we are depending on this measurement record, what one can do is that one can apply a feedback, right? So let's say I'm obtaining a measurement record dr, and I want to do something based on that measurement record. But since the dynamics that we are following is Markovian, the best thing to do in this scenario would be to apply a Markovian feedback. The feedback that only depends on the previous measurement record, not like all from the history. So to do that, what we do is that we just do a Markovian feedback, which depends. So d rho f depends only on the previous density matrix, not on the history of density matrix. And kappa is the super operator, which depends on the feedback force f. So the f is the feedback that you apply to the system. And if you do so, then the density matrix changes to this form, but still, I mean, one can just employ this density matrix and try to put different feedback and try to see what one obtains from this feedback mechanism. But for simple scenarios, we wanted to start from a very simple scenario. We said, okay, we have a measurement record, we have density matrix. What we do now is that we just apply a unitary feedback instead of all this Markovian feedback and more complicated scenarios. So if you do unitary feedback, you can say, okay, I have rho tilde equals to u rho u dagger. Then suppose I have couple qubits, then I have like 3 different states, 0, 1, and 2, and their probability would be P0, P1, P2. And what I do is that I rotate this P0, P1, P2 by a unitary matrix on both sides. So I'm just saying that U in this case is just like, U feedback is just that matrix on the right-hand side. And what it does, it just rotates the probability matrix or the density matrix. And depending on the value of theta, you have different combination of P1 and P2 as a feedback. Now, the first thing I do is I do a swap operation in the sense that I put theta equals to pi by 2, so that I'm swapping the two probabilities. P1 goes to P2 and P2 goes to P1. And this swap operation, we see that on the right-hand side gives you some cooling. And that's interesting because you see from the black dash curve, which is the average without feedback. So if you just do measurement, you don't get any cooling. It goes to below 0. So instead you are heating the system, right? But with feedback, that's like the curly curves, which is like individual realization, and the longer dashed black curve. You see that you get positive value of JR, which tells you that you're getting cooling when you apply feedback. So measurement plus feedback, this combination gives you cooling compared to no feedback at all. Now, these are comparison as a function of theta. Last time I just showed you the results for theta equals to pi by 2. Now I'm interested in looking at what happens to the cooling when I go through the entire range of theta, right? In the first plot, it looks like, so when theta equals to 0, the only cooling you obtain is due to measurement, because in this kind of system where you have two baths, you can also obtain cooling without feedback. But you see that when theta equals to pi by 2, you get the best measurement. And at the optimal, on the left-hand side, at the optimal case, when theta equals to pi by 2, what you see is that when you don't have measurement, you get better cooling, meaning measurement doesn't give you anything fruitful, in the sense that you don't need to do any measurement, just do feedback, and you get the best cooling effect. But that is not true in all the parameter regime. On the right-hand side, what you see is that there are parameter regime where measurement plus feedback helps you get better cooling effect. So if say theta equals to pi by 2, the purple curve is without measurement and the red curve is with measurement. And you see that when you have measurement plus feedback, you get better results compared to just feedback. So I think this is the last part, and I don't have a lot of results. I just have some results on power, but we are trying to use also reinforcement learning, machine learning to calculate what is the best choice of continuous actions like the qubit gap, the coupling time to the bath, the feedback strength or angle, and what is the optimal choice of discrete actions like attaching or detaching a bath to the qubits, or the measurement probe to study the optimal performance of this kind of machines, like what is the optimal power and what is the optimal efficiency of this kind of machines, and how do you tune different parameters to get that optimal value. And the goal is to study the optimal trade-off between power and efficiency. So the best trade-off between the heat extraction as well as the best efficiency that you can obtain with that heat extraction. And yeah, these are some results that I'm showing. Is like just for a single qubit case, we have some architecture. We recently built up our architecture also for like a power and efficiency trade-off. We have already something that can give us the maximum possible heat or maximum possible power of a system. We know how to calculate what parameters to choose to get the optimal values. This is a very simple example where I say, okay, I have a qubit and I have an environment. What is the feedback that I should apply? What is the unitary operation that I should apply to get the best output? And you see in the last, in the right-hand side, the bottom plot, that the best thing would be to do a swap operation. So you attach the bath and you do swap operation, you attach the bath again. So when you swap, you just supply the rest of the energy to the environment, you get the cooling effect. So yeah, this is still in work in progress. So mostly, yeah, finish very quickly. But so yeah, so these were like some of the works that were done, some of the works that were in progress, and the kind of a reporting instead of presentation, I guess. Thank you.
Okay, questions for Bibek?
Can you go to the coefficient of performance plots? Yeah, I'm wondering what is the difference between these three?
Oh, they are for a different initial state of the qubit. So G0 gives you the initial length of the qubit, right? So for different initial
So
block vector.
why, why do you get such high performance for some states versus others?
Because it depends on where you start from, right? The measurement depends. I mean, it's not that. So the amount of heat you extract depends on E0 minus EF, right? And it depends on gamma 0 in a very strong manner, G0. No, sorry, that's not EF. So it depends on G0, the amount of heat you extract from the system. So depending on where you start from, you get a different set of points.
Yes, so the highest ones, you start basically from a very high temperature initial state, right? So you're able to extract a lot of energy by purifying that.
Yes.
Go back to that plot we were Tathaga was just showing a moment ago. You mentioned in your presentation that the interesting feature here is that you would think that naively you just go to the extreme limit of projective measurement, and that gives you the best cop. But here you're saying that's not true, but you didn't tell us why. Why is it not true?
I don't know. I have to say, I didn't look into it in detail, but yeah, I don't have a right answer, but this is interesting in the sense that it could give us a way to look for optimization using machine learning, because we don't know that it's not straight. If it was like a monotonous curve, then it would have been very simple, right? You don't have to optimize over anything. But now, since it's like a non-monotonous curve, it's interesting in the sense that you can optimize over it, comparing it to the power extraction.
But it would seem that it's related to the fact that it's a ratio of two things, right?
Yes.
So the denominator involves the heat that is required by the measurement.
Yes.
So it tells you that at the ends there, you're putting more heat in than essentially you're able to.
Yes, that's the most I could say as well. Yes. So if you in the projective measurement, you are putting a lot of power to get not high enough refrigeration to balance that out, I guess.
Can you find the maximum of this, like the points where you get maximum for difference in or theoretical?
I think so. Yeah, it shouldn't be a very difficult problem. It's a very simple relation here, so it should be possible. We didn't do it, but I think we should do it. It's doable, I think.
Right. Other questions or comments? How about on the Zoom side, the Zoom people? We've got about 10 people on Zoom, so any questions from there? Maybe I can ask you a more general question. So you gave some presentation about trying to maximize refrigeration. Why do you want to do that? What's the motivation for trying to refrigerate with these quantum systems?
I think it's like interesting in the sense that refrigeration has been kind of like the basic building block. I mean, even in classical system, right? If you go to quantum system, I don't see why you won't be needing it as much as you need in a classical scenario. So I think quantum machines, or like if you like go to the quantum world, so to say, you will need refrigeration. And I think in comparison to bulk refrigeration, it would also be interesting to see how you can refrigerate like macroscopically, like within a local scenario. So these kind of machines would help, like how to cool the local stuff like in bulk.
Yes, so you showed this like this master equation where you include feedback for continuous measurements, and you talked about continuous measurement, doing continuous measurement for the part one, the single qubit case also.
Yes.
So is that the same thing you're doing there as well?
No, it's just the inter-rotation in the first part. So you just rotate the block vector in the first part, right, to the z-axis. There is no like Markovian. It's just nothing more complicated than that. In the other case, you also have, like, if you look into the dynamics, there's just not the unitary part. The unitary part is over there. You also have the other part that depends on F, right? The F, rho F, and any other parts. This is a more complicated dynamics, I would say, but still in the Markovian regime.
Yeah, one might naively think that just the measurement device could be modeled as simply another thermal reservoir. Right?
Yes.
But clearly you're getting features here that are not just thermal features, right? The fact that you can feedback and get cooling instead of heating, things like that.
Yes.
So what would you say is the principal difference between a measurement apparatus and just a thermal reservoir?
So there is a very subtle connection between the two. If you have only the sigma, I mean, it depends on what you are measuring. If you are measuring the right parameter, then you can be an infinite temperature limit of the thermal bath. But the point is that with the thermal bath, you can't connect it with all possible coupling operators in the system, right? Whereas with measurement probe, you can like measure any permission observable of the system. You can tweak your measurement probe to measure anything. And then you don't have one-to-one connection between the measurement probe and the bath in that limit. So in some limit, like in this case, I think the first one I showed here, this thing you can obtain also with a measurement. Instead of a measurement probe, you can take a bath with infinite temperature. You will get the same result. No difference here because that operator, sigma x operator, if you measure that operator, it's like just coupling the sigma x operator to the bath, right? That's just tunneling from the bath to the system. So you have the same results, but it's not one-to-one.
Can you show the expression of kappa you wrote with gamma delta T?
Yes.
So gamma delta T could be anything, right? So can kappa be less than -1 or greater than 1?
I think kappa is bounded by, yes, but I think it's when you go to 0 and 1, you reach the projective measurement limit. So what's stronger than projective, I think, is the undefined. So gamma delta T should be suitably chosen to be within that.
Yeah, I think this formula is applicable when gamma delta T is small.
Yes. Delta T is like the weak measurement, and time, and then gamma gives you the strength. So they are kind of inverse of each other. If you want to increase one, then you have to decrease the other one. Be within the regime.
Okay, other questions or comments?
I have a comment.
Yeah.
So you only consider unitary feedback in all of your situations?
For time being, yes. I mean, we're trying to do something more on feedback thing, but for time being, we just have unitary feedback.
And the measurement, that's not changed like over a sequence, or that's just kept the same?
Measurement is kept the same, it's not changed. That could be, I mean, that's like a bit more complicated problem, and that would go more towards machine learning stuff, where we can like play different parameters, try to see how you can tune measurement system parameters to get the optimal results, right? But doing those things analytically would be a difficult problem, I guess.
Yeah, so I guess in that case, you can think about the unitary feedback as a time-dependent Hamiltonian.
Yes.
So in that sense, you say that the cooling comes from the work you put into the feedback?
Mm-hmm. Yes.
This is the sort of first law explanation of that.
Mm-hmm.
All right, well, let's thank Bibek again for the seminar. All right, and Bibek